Good morning, everyone. Welcome to day 2. I'm excited to be going first this morning. Thanks to Adrian and Sunny and the whole team for organizing this fantastic event. I'm going to be telling you a little bit about some of the work we've been doing at Wayve the last few years and where this space is heading. So, the open road, the blue skies, the thrill of acceleration as you floor the accelerator pedal to the metal. The reality, unfortunately, looks a lot more like this for most of us on a day-to-day basis. The average American driver spends 2 full days of their lives stuck in traffic every year. Wouldn't it be great if we could get that time back for leisure, for work, to talk and play with our families? More seriously, we pay a huge toll as a society for our mobility. These are some of the statistics from the WHO on road safety. And, you know, this is all stuff that, this is a major cost that we pay. And the vast majority of that comes from human error. Things like speeding, aggression, recklessness, chemical impairment, distraction, and drowsiness. Robots don't have these problems. And so I stand here asking the question, wouldn't it be great if cars could drive themselves? I'm not the first to have asked this question by any means. But this really has been what I would describe as a space race, the space race of our generation, over the last 10 years, certainly. Now, despite enormous progress, and I took a Wayve vehicle from Sunnyvale to downtown San Francisco last night. Beautiful ride on the 280, absolutely stunning performance. I see Waymos everywhere around the city streets here. So there has been progress, and yet I think we'd all agree that it is far from ubiquitous. Autonomous vehicles are available to limited people in limited locations today. Why? What's been the challenge here? Well, I think for anyone who's worked in the industry, you will appreciate just actually how hard this space is. It is just, first of all, fundamentally an incredibly hard problem. But I think we lost years, if not a whole decade, following what I describe as the traditional approach, or AV 1.0. And now this makes superficial sense. If you look at what this is, this is how you'd start engineering this, and it makes total sense, right? You have some sensors, and why not throw as many of those as you possibly can at the problem, because they're all going to pick up on different things and add value. You're going to run some perception algorithms on this to detect the objects and the lanes and various other things you're going to need. Oh, and why not let's build some HD maps and map out whole cities in great detail. And then we can use that to localize where we are and know what to do, which lane to get into, which stop sign to listen to, etc. And with all of that, then we can build a planning algorithm, and we can, maybe we hand design that, maybe we even learn that with machine learning, and finally we pass that to a controller. So all makes sense superficially, and yet it has some real challenges, and history has shown that it is slow and expensive to scale. Yes, there are real deployments of this out there, and they are really quite good. However, they're not commercially viable, they're in limited locations, etc. And you can look at all aspects of the design space in AV 1.0 and spot the problems, the supervised perception stack that's brittle if you don't know what you're looking for. Hand design rules are very, very clunky and rigid. Now, most of that's got rid of these days. But it still remains as a brittle part of the stack. HD maps, they're very expensive to build and maintain. They're great if you've got them, but doesn't help with getting to ubiquity. And high-end sensors, or throw the kitchen sink at it, kind of works, but makes it very expensive and hard to deploy at scale. Now, simultaneously, over the last 10 years, something quite radical has been happening in the general space of AI. And here's just a few examples from the last few years. And this slide, I've given up updating this slide because it just, breakthrough after breakthrough after breakthrough. Amazing progress. And this has been driven by, all sorts of, core foundations of modern AI. That includes things like, large-scale data sets and benchmarks that have allowed competition in the community, things like games and simulations, which have allowed RL algorithms, for example, to thrive, self-supervised learning so that you can, you don't have to go and label a huge quantity of data, foundation models that, really build general purpose understanding of over large corpuses of data, scalable compute, the GPU, the data center at just insane levels now, scalable architectures that fit well onto those, like the transformer, the ability to now bring multimodality together, images, videos, text, language, etc. And all sorts of post-training tricks, RLHF, chain of thought, reasoning, etc. So, taken together, this has driven just enormous progress over the last 5 years or so. And here's just, a few of the benchmarks in the space of cognitive AI and the progress that's been made on those. And, again and again and again, we see this falling. I believe embodied AI is next. And I think you all believe this too. That's why we're here. Now, Alex, our CEO and co-founder of Wayve, had this vision 8 years ago. And the realization was that if you look at a driving scene like this is just a relatively run-of-the-mill day in London. This is not unusual to see this. The realization here is sensing the objects is not difficult. It's pretty easy to see there's a person there, there's a car, there's a van. That's not difficult. The difficult thing is deciding what to do, how to act in this crazy unstructured environment. And, and so we set out with Wayve to build autonomous driving and solve it as a true embodied AI problem. And what this means in practice is throwing away all that horrible complexity of the AV 1.0 stack and building an AV 2.0 stack where we take sensors and we can be as light or as heavy as we want to, flexible there. An end-to-end AI that is literally just an end-to-end big neural network. And pass that into the controller to actuate this on the vehicle. Now, there are some differences, right? Some big differences, and I'm sure all of you probably who've been working in this space will have come across some or all of these. Data, where do you get that from? You can't just scrape the web. There's potentially many different tasks you need to do, many different modalities you need to think about. Training compute, well, we're dealing with high-dimensional video data, sensor data. That gets expensive compared to language. The physical embodiment, of course, right? Robots don't do what you ask them to do all the time. You've got to fit on an embedded processor that ships on the robot. And you're ultimately out there in the real world, being able to operate around humans in an unstructured environment that's safety critical. Measurement's really hard. The world doesn't do the same thing. It's very hard to repeat an exact experiment, certainly on the streets. And of course, you've got to build trust in what the output of this thing is. It's got to coexist with humans, and they've got to believe it's safe. They've got to trust that that's going to work, and understand why it works. But we've been working on all of these problems for the last 8 years, and really, even the last maybe 1 or 2 years, we've hit real inflection points in the quality and capabilities of the Wayve AI driver. A year ago, well, maybe just a little bit over a year ago, we only could drive in the UK. And the last year, if I could sum it up in a word for us, has been generalization. We are now able to drive across multiple continents. We've driven in hundreds of cities worldwide, across probably 10 plus different vehicles at this point. And it has really been, both surprising but also really heartening to see that our thesis that this is going to be the way we scale up autonomy across the world has panned out, that AV 2.0 approach is going to work. And as a business, I mean, our primary business that we're building towards right now is in the automotive sector, selling our AI to OEMs and selling it as a safe driving intelligence that's designed to accelerate the transition from ADAS, automated driver assistance systems, advanced driver assistance systems, to all the way to L3, L4 driverless deployments. And the approach is brilliant because it really fits their needs. They can take their existing vehicles, their existing hardware setups that they've been building over the last few years with the sensors they need. We can slot into that very easily and quickly into those vehicles. We don't need these HD maps, so it's very easy to deploy at broad scale. And as I say, we're laying the foundations for nearly a software update to get us all the way from L2 up to L4. So on this journey of generalization over the last year, we did some interesting experiments. And the first was going to the US. So we started in the UK. That's where our headquarters has been, and where our core competency of driving in London has been, as you see in the top here. Now, when we first got to Silicon Valley and started deploying this on the road, the first thing we tried is, well, let's see what happens out of the box. Zero-shot driving. Unsurprisingly, having only driven on the left side of the road before, doesn't do too great to start with. And so you see this big drop from our UK performance of zero-shot. But what was really heartening, as soon as we start adding relatively small amounts of data, 100 hours, 500 hours, we see massive improvements and really starting to close that gap very, very quickly. And that results in the kinds of drives that you see in the bottom here and I was taking yesterday. What was even more exciting, though, is when we went to Germany, which we did, I think late last year, and here we can see the zero-shot US was significantly worse. When we went zero-shot Germany, there's still a gap, but it's much, much lower than it was when we went to the US. And this is telling us that what we've learned in the US and the UK is now helping us in new geographies. And now we're seeing this time and time again. We've now gone to Japan. And here's a little snippet of some driving around the crazy streets of Tokyo. Similarly, the performance, the generalization gets better each time. This is a little fun one on a mountain road in Italy. All of these results are the same driving model. The same model can drive in all of these locations. We don't have to. We do tell it which country it's in, but other than that, it's the same driving model. Here, hairpin turns on steep mountain road. Beautiful. We'd never driven this before. It just works. Another fun one here, the so-called magic roundabout in the UK. I don't know who designed this or what they were thinking, but it exists. It's a real place. And here we go, seeing our car navigating this. You have sort of regular roundabouts on the outside, and then on the inside you go counterflow. Somehow, people manage to do this, and our AI is, equally capable. And of course, France has their equivalent, right? Here's the Arc de Triomphe in Paris, and this is sort of similar in a different way. Another big roundabout. Basically no structure at all, no lanes, crazy traffic coming from all directions, going in all directions. Try doing this with a traditional stack where you have to detect lanes and expect traffic to follow particular patterns. That's not how the real world works, at least not everywhere. And so here again is our driver safely navigating around this crazy part of Paris. Now, that was all about geo-generalization and the scale-up that we've seen there. This next video is about the crazy things that happen on the road that are, this is, not geo-specific, but this could happen anywhere. So, animals, horses. We haven't done anything to train for horses. We haven't done anything to train for squirrels. Go-karts? Sheep? And the beauty of the approach that we've taken here with AV 2.0 is that you don't have to train for these things. These things emerge. It learns, it's able to learn that there's this concept of obstacle and that you shouldn't drive into obstacles. If there's an obstacle in the road, a duck, for example, you wait for it to get out of the way, or you find a way around it if appropriate. And here again, the busy streets of Tokyo and navigating these really tight roads with bustling traffic, human traffic, or navigating around, construction, narrow areas, squeezing through these small gaps. So all of that has, of course, been exciting our OEM partners, and the first to announce our partnership publicly is Nissan, where just 2 days ago they unveiled the next generation ProPilot, which is going to feature our AI in a couple of years on their vehicles. We're super excited about that. This is just the tip of the iceberg in terms of where we're going to be deploying. And we also had a visit from Jensen last week in London, who gave us a Thor and a check, which is always appreciated. So moving on, I'm going to just talk about a couple of areas that I find particularly interesting. One is around language, and the other is around data. So, if you look at LLMs, large language models, they are capable of, they know a lot about driving. And you can ask it questions. You can ask ChatGPT questions around, what should you do in certain situations on the road. You're driving along a road, a ball rolls out in the road in front of you, what might happen next? How would your answer change if you were driving next to a school? And how would it change further if it was midnight? So, and the answers, I won't read them out here, but they're pretty plausible. It clearly has a reasonable understanding about what's going on. And I think there's all sorts of applications. The one I'm just going to touch on today briefly is explainability. Can we get a language model to describe what it's seeing as we're driving and explain what's happening, what's important in the scene? And so here's a few examples from Lingo 1, which we put out a couple of years ago on captioning, on how, describing the scene that it's seeing. So the top left, let's say I'm turning right to continue my intended route. Top right, I'm staying stopped because I still don't have the right of way, and eventually that will change here we go, I'm turning right because the lane is clear, etc. There is, this is really, really interesting. We also turned this into a chat interface. Oops. Hopefully this is going to play. Yeah, here we go. So what are you paying attention to? Currently, I'm focusing on the drivable area, and it then refers to what it's seeing in the scene, that area A. I'm also monitoring the traffic B and the lead car C. So it's able to connect the visual scene and the driving decision-making and allow you to sort of question it and ask really interesting things. We then took that and combined that was an offline model, Lingo 1, into Lingo 2, where we actually had this in the same model that could drive. So it was driving and able to caption at the same time. So here, increasing speed, making a right turn to stay en route, reducing speed for the upcoming turn. In fact, one of the problems is it's updating its text so frequently it's hard to read out here. But gives you a flavor of really interesting insights into what could be happening in the robot's brain. The other topic I want to touch on is data, and especially when it's hard to get. So, everyday driving, you'll see a lot, but there's this, concept of the long tail, the things that are very rare that you're not going to see very often. Now, you can drive a lot, you can scale up your fleet, wait a long time, or you can try and find other ways to get this data. So how do we get the kind of these kind of crazy double overtake things or these cut-in, how do we get data for these kind of scenarios? Well, these examples here are actually all synthetic. They've been generated with our system Gaia 2, which is generative AI for autonomy. And Gaia 2 is a generative AI that generates photorealistic, multi-view synthetic video with a huge amount of controllability and geographic diversity in there, trained off the data from our globally diverse fleet. And it has all sorts of fun properties. I won't go into the architecture in any detail, but you're welcome to check out the blog and the paper, the tech report on Archive. But it's capable of some amazing things. So first off, it can do generation. So from scratch generation. So these are all examples. The rows are different examples. The columns are different camera views. And here we've just said, okay, generate us a scene in London or Germany or the US. And it's able to generate a huge diversity of stuff, different road layouts, traffic conditions, weather conditions, times of day, etc. We can ask it to generate variations of specific scenarios. So here we prompted it to ask her to generate overtake a bus. And so, lo and behold, it creates a hypothetical world and generates examples of us overtaking those buses. You can also, here's another example where we're generating U-turn scenarios. And again, you get the scenario you want, but you get a huge amount of variation. Where it gets really interesting, though, is the safety critical aspects, the ones you don't want to see on the road. You never want to get into these situations. And so here's one where we can control the ego vehicle to drive it into oncoming traffic. Gaia is a true world model, so it's not just arbitrarily generating future videos at whim. We get at every time step the ability to control the ego vehicle and indeed other aspects of the traffic. Here's another example where we are getting the lead vehicles to brake suddenly. And this is sort of super useful for queuing up emergency braking capabilities. Beyond just generation, we can also do scene editing. So here's a few examples where we start with the image on the left. So here's an original normal driving, just driving behind a bus. And we can turn this into something quite dangerous. So here, the bus brakes suddenly and we accelerate as an ego vehicle. Here's another example where, on the left, we've got the original real scene where we do a sort of, fairly gentle overtake or initiate of that. And now we can turn it into something quite crazy where we accelerate the ego vehicle radically. All the rest of the traffic's playing at the same speed, but we're going super fast. Another example here in Tokyo, we turn a corner and just drive straight. And we turn that into something where we veer quickly across into the opposing lane. So this is, really, really useful capabilities for generating unusual edge cases that would be very hard to see on the road. Now, this is a real video this time, not a generated video. And this is on a test track, and it's an example of our emergency braking AEB system that we've built. And what's really exciting for me is that this is in significant part trained on some of the synthetic data that I just showed you, that is allowing us to train these systems, even though we haven't had to go and crash into a bunch of vehicles to get that data. Beyond the safety critical scenarios, which are super important, there's also a general ability for us to use Gaia and derivatives of Gaia to expand the value of the data we have or we can get. So in this example, you can imagine getting, say, dashcam footage off the internet And we can now take that single view data and we can turn it into full surround, spatially consistent, temporally consistent multi-view imagery. I think this is like a phenomenal capability. Another variant of this is to take depth images or LiDAR scans and to turn that into, again, surround RGB. And so this is an example where that little inset picture-in-picture is the input, and then the big RGB multi-view images is the output here, where we're now deliberately sort of weaving the vehicle on this road. And finally, we can start to generate some really crazy outer distribution stuff. So here we're going to start the vehicle, and then we're going to steer the ego vehicle off the road, across the traffic, into the grass, and off into the forest. So maybe this is going to start to open up some exciting opportunities in off-road driving. So I'll start to wrap up. Wayve is paving the way for safe and scalable auto-grade AI. And stepping back, more generally, embodied AI is really promising to transform how humans interact with technology. And the decade ahead is going to be transformational in this regard. We're building towards that future at Wayve. We're starting with automotive, but we're scaling up beyond and building a foundation model as a true platform for embodied AI across multiple different input sensors and tasks, different output tasks and applications. And stepping back about like how do we make this a success as a community, as a robotics community? Well, here are a few things that I think are really important. Whatever we build, it's got to slot into our messy world. We're not going to change the world radically for robots to get it out there at scale. The world is going to be the same. We have to adapt with our robots. We've got to build businesses. It's great to have an amazing VC community and money that flows in to get us off the ground, but we've got to turn these into viable businesses that are profitable and scalable. We've got to be accepted by the public and by regulators. There's no good building this if that doesn't happen, because it will just get shut down, won't work. And relatedly, of course, you've got to then meet human safety expectations and reliability expectations. It's got to interact with the human-machine interface. Really does matter here. But of course, ultimately, it has to add value and utility to our lives. Well, with that, I'll say thank you very much.